Finished?
Why can't you use visible light to see molecule?
Yeah, why?
Because
Yeah.
visible.
Yeah.
The visible light is we have used more frequency something.
Yeah.
See
The problem is
visible light is
the
not enough frequency.
yeah, you can just say the wavelength is too big. That's fine. Okay, last question, and then we'll do the next lesson.
Radiation.
Yeah. That's another name for electromagnetic wave.
I know we have can see light on shorter wavelengths than shorter, so maybe what's this? Capillars. You mean radiation is wavelengths?
Good. Correct. Alright, let's start the next lesson. Got that? Yeah. Okay. A lot to do. A lot to do. Okay, so the first word, reflection. I think you know this word. What does it mean? Reflection.
No.
You don't know this word? New word?
I've seen this before.
Yeah.
I don't remember.
Okay. Reflection is the change in direction of a wave at a boundary between two different media so that the wave moves back into the medium it came from. The most common example includes reflection of light against a mirror, sound and water against a wall. Reflection. So, it's the change in direction of a wave at a boundary. This is the boundary between two different media so that the wave moves back. So the light goes out and comes back. The most common example is reflection of light. but also reflection of sound. So when I'm speaking, my sound wave reflects from the board. You know, so this is reflection. So you can just write this much. Yep. And also, draw the picture. Beautiful. Great, great. Now, the next one is diffraction. So diffraction occurs when waves bend around small obstacles, or when waves spread out after they pass through small openings. Here's an example of diffraction. So we say that the wave is diffracted as it passes through a small gap. It diffracts more than when it passes through a large gap. So this process is called diffraction. This is a little diffraction, and this is a lot of diffraction. Why? Good question. Good question. I think it's because the wave is traveling like this. So if you close it, then what will happen is a small piece will pass through. But I think it will still try to make the same circle. So if you look here, this little piece of the wave becomes bigger because it's the same over a greater distance. So I think all that's happening is the wave always does this. It always spreads out. It's just you see a little piece of it spreading out. I don't know, Ben, but this is my guess.
Okay.
Anyways, if you can write and draw this.
And why the left is just this
What do you mean?
life side,
The size?
life side.
Left side? Right side?
I mean, left side is straight.
Here?
Yeah.
Well, it's not, it's a wave. It's a longitudinal wave. It's vibrating like this.
The same. This.
They're both the same.
Oh, you just straight line.
No, it's a, yeah, I know what you're saying. It's not this wave, it's this one. The one that's like the sound wave. These lines represent the crest, yeah?
So in this,
Yeah.
we just talk about this.
Oh good, sorry, yeah, I understand now. Let me think. Yeah, for this one it could be both. It's just in the picture, This is the picture of longitudinal waves.
But we know in class, if we have this
The polarizer.
the trans something light will be blocked, and if this will pass and move.
Good question, Ben. Good question.
Like this.
Okay. So Ben, the difference, when you're ready, I'll tell you.
Okay.
So if you give me your notebook. So in this picture here, the light is moving in all different directions. And when it passes through this, it doesn't diffract, it polarizes. Now, if you were to pass this again through this, it would diffract. Because in this picture here, this is already polarized. It's only moving in one direction. It's not moving in many directions. So you could do this first, it'll polarize. Then if you do it again, it will diffract.
Okay.
Yeah, so that's the difference. Yeah. Good question. Can you draw this as well?
But I need to draw the straight line.
I'll just draw this one.
I think the straight line is so confused.
Yeah, you think so? Oh, I think it's better.
It's okay.
These lines mean crest, and this means trough. So it's like up, down, you know?
Oh.
Crest, trough, crest, trough. Yeah? No?
Why? But you get away, but you know this.
Yeah, yeah. It's hard to draw this.
Okay.
That's why. It's difficult to draw this. It's easier to draw this. It's difficult to draw this, you know. Okay, next one. Refraction. Refraction is the change in direction of a wave caused by the change in the wave's speed. Refraction is seen most often when a wave passes from one medium to a different medium. So here's the famous example. So here you have air, and here you have glass. And the light passes from the air to the glass, it refracts. It means its direction changes. And then if it passes from the glass to the air, it refracts again. You in the picture? Yep. Great. Okay. Some materials will allow light to pass through it more freely than others, whereas some materials will slow the light down. For example, light moves slower in glass than air. So if we go back to the last picture here, here the light's going fast. When it moves in the glass, it's going slower. It actually moves slower. And there's a way to measure this. We call it the refractive index. The refractive index of a material is a measure of how fast yellow light can travel through the material. Mathematically, it's this formula. It's the C over the V. So for example, let's say you have something like glass, and here's the light, and it's going 3 times 10 to the 8, that's C. And here it's going 2 times 10 to the 8 inside. So we say the N is C over V, which in this case would be 1.5. So the bigger N means it moves slower inside. Yeah. Now, C is the speed of light and V is the speed of light in the material. N is between 1 and infinity. Yeah. N equals 1 is a vacuum, empty space. And N equals infinity means the light has stopped moving. Yeah. So if you can get this definition now. Got it?
Oh, and the last, therefore.
Yeah? Got that? Okay. Now, Snell's law is a way to calculate the refraction angles. And Snell said that sine theta 1 over sine theta 2 equals n2 over n1. And there's a nice picture here that explains the angles. So what happens is, oh, I don't know if you can see that so well, that's theta 1 and that's theta 2. So the light comes in at theta 1 in material n1, and it leaves at theta 2 in material n2. Okay? Now please, this is important. For example, here is air and here is water. We always measure the angle here to the normal. We never measure the angle here. Don't do that. Okay? Huh?
Why?
The rule, Snell's law, is for when theta 1 is measured from here. And then here is theta 2. And this is n1 and this is n2. Okay? I think, Ben, if you use this angle instead, then I think the sine becomes cos. I think. Yeah. Yes.
Well, maybe.
But don't do that. They always want this angle and this angle.
Why 2 theta is 2?
Theta 1, theta 2.
Oh, it's 1.
That's a 1, yeah. Theta 1. It looks like a 2. Theta 1, theta 2. This is Snell's law. It lets you calculate the angles. Yeah? Okay. Go. You can write it down now. Yeah, okay. Now, under certain conditions, it's possible to choose an angle theta 1 so that theta 2 is 90. So what you could do, it's possible, you could have the light come in, we call this angle C, and instead of going in here, it goes along here. So this is 90. So according to the formula, it's sine C over sine 90 equals n2 over n1. Yeah, that's using Snell's law.
N1 is 1.
No, because this could be like water and glass,
Oh.
you know. Sometimes it's 1, yeah. Sine 90 is 1.
Yeah.
So that means C equals sine inverse n2 over n1. But this only works if n2 is smaller than n1. Because of the sine inverse, this number must be less than 1. You know? You couldn't do, for example, look what happens here. Press equals. No answer. No, sine inverse. Inverse. Shift. See? So this is called the critical angle. Okay. So here's if n2 is less than n1, then the critical angle is sine inverse n2 over n1. Yeah?
Maybe normally N1 is the air,
Normally, yes, then no critical angle.
but normally, just for example,
Yeah.
this N2 is water, but I think N2 is bigger than N1.
It is, so you can't do it. But you could do it the other way.
Only this way.
You can only do it water to air. But you can't do it air to water. It's not possible.
Okay.
Yeah. So the n, you need to start with the bigger. You need to start with the bigger and finish at the smaller.
Useless.
Useless? No, not useless. Not useless. This is called total internal refraction. Not useless. I'll tell you where it's useful. Okay? Do you know the fast internet fiber optic? Do you know this word? You got your dictionary? You got your dictionary? This cable uses lots of glass and it uses internal refraction, the critical angle. So it's important for this. Okay, can you write this down? Including this.
Why they use glass?
I don't know. Maybe they use plastic. No, plastic maybe is no good. What's wrong with glass?
I don't know why they use glass. Will quickly or just slowly?
A little slower, but still fast. Maybe they don't use glass. Maybe they use a different material. Because I feel like glass would break.
I think maybe I guess it's something. This.
Yeah.
I guess.
No, maybe. Maybe. Yeah, maybe. I don't know. Maybe.
I don't know.
Okay. This, and you also need these words.
All of them.
No, the red. Critical angle is the C, and this whole process is called total internal refraction.
Theta 2 equals 90,
Yes,
and so we can use this.
yes. To get theta 1.
Okay. So it means the light can be block.
Kind of like block, yeah, the light comes in and then moves across the boundary. It doesn't,
Yeah.
and if you have more than C, then it comes in and comes back. Mm.
So remember the right one.
Say it again.
Right holding.
This box
Yeah.
and these two words. Critical angle is the C. Total internal refraction is this whole process.
No 19.
No what?
19.
No. Yeah, okay, right, theta 2 is 90.
Critical. I know critical. Some critical thinking.
Yes.
Is this word?
It's the same word, different meaning.
Okay.
Yeah? Okay, let's continue. Notice in the last lesson you did not see white light listed. That's because there's no frequency for white light. We have frequencies for red, orange, green, etc., but none for white. That's because white is a mixture of all the colours. So, basically what I'm saying then is if you take red and you also take orange, yellow, green, you take red plus orange plus yellow plus green plus blue plus indigo plus violet. You add all these colours together, it will make white, which is the colour.
In the real life, I mean, you know the tall.
The what?
Tall. Something like the ground something. Okay, fine. Just I mean, is make the color then will become black.
Ah, black.
Black.
Which? How would you make black?
Just make. I think it's make the whole all of the color.
Yeah, that's only true if it's paint.
Yeah, I mean it's pink.
If it's paint, it's black.
And
But if it's light, it's white.
okay.
Yeah, I know. If you mix all the colours for paint, you get black. But if you mix red light and orange light and yellow and green and blue and indigo violet, this will make white light. Now, see this light up here? That's white light, except it has a little too much yellow in it.
Oh, yeah.
So it's kind of,
Orange.
yeah, kind of too much orange, too much yellow.
Is one.
Whoops. Yeah.
One.
Wrong, yeah. The sun is more like white light. Now, it's not perfect. It's a little bit different than white, but it's nearly white light. Yeah.
It's too different.
Yeah, this is maybe more white. Yeah, yeah. Okay. So, look at the picture here. If you have white light and you put it into a prism, then you can get all the different colours. But if you look at Snell's law, sine theta 1 over sine theta 2 equals n1 over n2. The theta 1 is the same for all the colours, but the theta 2's are all different. Now, why are the theta 2's different? This is the same, this is the same, this is the same, so shouldn't this be the same?
No.
Yeah, what's wrong? One of these is not the same. And it's the N2. This is different for different colours. So if you go back to your definition for N, here, this is only for yellow. Did you write down yellow light?
No.
Oh.
This one.
No, this one.
Not this one. No.
Ah, no, you see, that was important, Ben. So this N, they calculate it using yellow light.
Oh.
Yeah? So this,
Only yellow.
well, the definition is for yellow. So usually what happens in the exam is they say the refractive index N and they tell you what colour it's for. So they might say N for red light is 1.5. For yellow light it's 1.6. Is it different for each colour? Okay. Now, the other important thing to know in this picture is that the F does not change. Okay? So the frequency here and the frequency here is the same. And the reason for that is, in this picture here, you have high energy, and here you have low energy. And you have low energy because you have a low frequency. And you have high energy because you have a high frequency. So what's happening is, the frequency doesn't change because the energy doesn't change.
Yeah.
That's why the frequency is the same. So, just to recap here, we can say that the N depends on the colour. Okay? The V can change. The F is constant, and the theta can change. And also, the wavelength can change. So this is constant. The V can change, the theta can change, the lambda can change.
N is N
Yeah. I suppose if you want to say it. We could maybe say that a little bit better, Ben. Thank you. We could say the n is constant for the colour. Is that what you mean? Yeah. I think it'd be good if you write this down. Oh, okay. Yeah? Okay. There's actually 3 ways to say Snell's law. The first way we did. Okay? But there's another way to say Snell's law. You can say that sine theta 1 over sine theta 2 equals lambda 1 over lambda 2. And you can also say sine theta 1 over sine theta 2 equals v1 over v2. Please be careful with the 1s and the 2s. This is 1, 2, 1, 2, 1, 2. This is 2, 1, 1, 2, 1, 2. Be careful. Oh my goodness, excuse me. Continue. Yeah? 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 Okay, good man. Right. One use of Snell's law is in a lens. When light enters a glass, it will refract, but the lens is curved, and this will result in different theta 1s and theta 2s. So I'll try and explain this with a picture if I can. Okay, so I always have a hard time drawing these. Alright, so this is glass, N2, and this is air, N1. So if it comes straight in, it just goes straight through like that. Now, if it comes in at an angle, here's the angle here. You can make the shape so that when it comes out the other side, it meets at one point. It's really hard to explain, but you can very carefully make the curve here so that the theta 1 and the theta 2 make sure that the light... No, hang on, sorry. That's terrible. It's terrible. Let me try and draw this again. That's absolutely terrible, right? Right here, here, and here. So here's the normal, here's the normal, and here's the normal. So in this one here, theta 1 maybe is 0. Okay. Here maybe theta 1 is 45. And here theta 2 maybe is also 45. Okay. And these lines are parallel. So what you can do is you can make the shape so that when it refracts and refracts, they can all meet here. If the theta 2 is the right angle, you can make it meet at one point, as long as if it's the correct shape. So this is how the lens works. It refracts all the light to one point. So what you could just say is, you could just write down, you don't need to draw this, one use of refraction is in making a lens, this is called a lens, focus light on one point. Yeah, I think if you can just write that, it would be good. Okay? Right, now, we have a question here. What I'm thinking is, we'll do this question and finish. Okay? Right, the speed of light in red light is 2 times 10 to the 8. What is the refractive index of glass? Okay, well, this is easy peasy. N equals C over V. Yeah? So what would it be for this one? It'd be 3 times 10 to the 8 over 2 times 10 to the 8, so that's 1.5.
Okay.
Okay? Alright. The refractive index of air is 1, N1 is 1. Red light enters the glass from the air at 20. What angle does the light travel at as it enters the block? So my question is, here's the block. The light comes in at 20. And my question is, what's the theta 2 here? And this N1 is 1 and N2 is 1.33. Okay, so let's calculate this. We know the formula. It's sine 20 over sine theta 2 equals 1.33 over 1. Will I use this? Sine 20 divided by 1.33, sine inverse, and that's 14.9. Okay, and the last part, part C, this time the light tries to leave the glass, but then it doesn't because it's at the critical angle. And the question is, what's the critical angle here? So that's just C equals sine inverse 1 over 1.33. Yeah. It's fine, isn't it? 48.8. Okay, Ben, once you write this down, you can go. Huh? It's very messy. I'm very, very messy.
V2 equals 2 times 8 and 2 equals 1 times 3 equals 1 and 3.
Yeah. Okay. Did you ever get a message back from Khalifa, Summer, or Gao? Did they reply to your message?